Hi there, this is my lab where I've been designing quadcopters, computers for quadcopters, and doing it from scratch. So I'm down today because I had a fire on this one today. Have to get a new motor controller, so I'm down for a few days. So today I'm going to go through and give you a lesson on how to get started if you're going to design your own quadcopter, just going through the optimization, the engineering aspects of it. Not as much as going through the physical implementation, but just going through the physics of it. So this is my lab where I've been designing various quadcopters. Haven't been so successful yet, but I'm getting there. And just wanted to show you some of my scrap pile here that I use for spare parts. Okay, so today we're going to talk about how to analyze, design, and model a quadcopter airframe, Part 1. So the purpose of this paper is to teach you how to analyze, design, and model a quadcopter airframe. A spreadsheet is used to initially examine the forces and torques applied to the airframe. This information will provide an analysis method used to design and size the quadcopter and to provide a 6-degree of freedom dynamics simulation model of its airframe, motors, and propellers. The control forces and torques are examined to determine if they are great enough to balance the quadcopter airframe to determine if the design is feasible. The control laws for the quadcopter will be addressed at a later time. It is assumed that each of the 4 motors will be commanded by providing an RPM command, which then each motor will turn each propeller at the commanded RPM. Example calculations for this example are performed at sea level to provide one design point that is used to verify the calculations in the spreadsheet. Parametric analysis can then be performed to optimize the design. In this paper, it teaches you how to get started if you're going to design a quadcopter. Now, one of the big problems when you buy a quadcopter, a lot of the software is proprietary. You can't get into it to figure out how it works. I know a lot of them fly very well. So the object of this is to start from scratch so you could get a good understanding to build your own airframe if you wanted to do something special that you can't buy off the shelf. So a lot of work went into the off-the-shelf ones. So I'm trying to design a similar thing and maybe reverse engineer some of them to understand what they're doing. But in this case, we're just starting from scratch, like a complete whole new design of the quadcopter. So in this video, in this lesson, a spreadsheet is used. So we use a spreadsheet to examine the forces and torques applied to the airframe. So this is the method that we're going to use to determine if it's a feasible design, and also allow us to provide a 6-degree of freedom dynamic simulation of the airframe, motors, and propellers. So the control forces and torques are examined to determine if they're great enough to balance the quadcopter airframe to determine if the design is feasible. So this part is important to figure out, do we have enough thrust to be able to lift the weight of the unit? Is there enough control force to pitch, roll, and yaw the quadcopter? So the control laws for the quadcopter will be addressed at a later time in later parts of this analysis. So I'm going to just present this without the control law part. So later on we'll look at the control laws and try to get understanding of some basic control laws that we could use to control this quadcopter. But right now for this analysis, we're just looking at it at a higher level just to get the initial airframe design. So in this quadcopter design, we're assuming that we provide the motors an RPM command, which will command each motor to turn at that RPM that's commanded. So it's kind of like an RPM is proportional to power. So as you turn the RPM up on the motor, well, of course the torque increases also. So the torque times RPM is the power. So we're looking at it as the way these propellers work. We'll see in the analysis that RPM and power are related to each other. They're sort of proportional. So we'll show how that works in the calculations. So we're doing this. We're going to do one calculation at sea level So if you want to do higher altitudes, what it is the air density changes. It gets the air density gets smaller, which changes the performance of the quadcopter. So we're just going to do one point here, one design calculation, one design point to look at, and then it's going to be put into a spreadsheet, into a column. So you can later then look at the columns. You could vary anything in the column so that you can do kind of a parametric analysis. So we could vary different things to try to optimize design to get the best design that we could possibly get. So one of the first things to do is to draw a diagram to understand the physics of the quadcopter. I made a diagram, and this is a top view, as if your head is in the sky looking down onto the airframe. So the blue lines here represent the airframe. So it's just basically an X over here. So we have some axes here shown by the red lines. So this would be our x-axis, and this would be, normally if we were to command the quadcopter to move forward, it would go in this direction as the x-axis is pointing. So we have a y-axis, which is coming out of the right side of the airframe, and we have the z-axis, which points down through the center of the airframe. So there are some parameters that we use in when we analyze airframes of aircraft. So on the x-axis we have these parameters x, l, u, p, and phi. So x represents the x force. That would be the driving force that causes the motion, the forward motion of the quadcopter. And L would be our roll moment, where the positive is rolling to the right. So it's using the right hand rule here. So this is the roll moment, L. And U would be the longitudinal velocity. That would be the forward velocity. And P would be the roll rate, again positive in this direction. And phi would be considered the roll angle or bank angle, positive in this direction, or right turn. So we also have our y-axis parameters here. So y is our lateral force that would tend to cause the airframe to move to the right. And m is our longitudinal moment, or our pitching moment, m, where positive is going this way using the right hand rule. V is our lateral velocity, which would tend to make the aircraft drift to the right. Q is our angular rate. It's called our pitch rate. So Q is our pitch rate, and again this is positive. And phi is our pitch angle, which this direction is positive. Nose up would be positive for our pitch angle, phi. So phi, and psi are sometimes called the Euler angles. So in our z-axis, z pointing down through the center of the vehicle is our vertical force. So this would be like the force we mostly have to counteract. We have to build up enough thrust to counteract the weight of the aircraft. So that's where our z force. So N is our yaw moment, and again it's turning right. Turning right is positive. And W is our vertical velocity, which going down it'd be positive. And R is our yaw rate, again turning right is positive. And psi is our azimuth angle, so that would represent the heading of the aircraft. Again, right is this way. So trying to get familiar with some of the parameters in our airframe model. So this aircraft, being a quadcopter, has 4 motors, 4 propellers, and so we call this motor A, and this motor B, this one's motor C, and this one's motor D. So we're assuming motor A has clockwise motion, and motor C also has clockwise motion, and motor B and D has counterclockwise motion. So the propeller turns counterclockwise on motors B and D, and on motors A, the propellers turn clockwise. So the counter rotation helps to cancel out issues with yaw, with trying to balance out the yaw movements. So motor A, the propeller spins at an angular velocity omega A, and motor B, the propeller spins at angular velocity omega b, and motor C, the propeller spins at angular velocity omega c, and motor D, the motor spins at angular velocity. It spins the propeller at omega d. So there's basically four forces: force A, force B, force C, force C, D. So we force A, B, C, and D. So these are the thrusts coming out of the propeller. So that's what the force is. So NA is due to the drag. So the way these quadcopters turn, it's not very obvious, but the way they actually turn, a lot of people might think it might be because of the change in angular momentum, but that all cancels out. So we assume that when we're commanding basically the average, the sum of all these RPMs are a constant. So what happens if you want to pitch down, we turn these motors up, and these motors, if we want to pitch up, say increase our forward velocity, we would increase the speed of these motors and decrease the speed of these motors. So it would cause a pitch down moment that's negative here, a negative theta, and that would tend to make the aircraft move forward. So what it is, the commands are kind of equal and opposite. So, but anyway, the way you turn, the way you for roll and pitch, those controls are pretty obviously easy. Like for pitch, if you want to go forward, we lower the speed of these two and increase the speed of these two, and that'll cause the aircraft to go forward. If we want to roll, we increase the speed of these two motors, A and D, and decrease the speed of these motors, and then we'll build up a phi, and that'll build up a lateral force, and the aircraft will move to the right. But to y'all though, what it is that there's a drag on these propellers. So the drag, aerodynamic drag. So we call this one NA, NB, ND, and NC. Okay, so the way we turn it is to get it if we want to yaw the aircraft, what we'll do is we'll increase the speed on these two motors, on FA and FC, and decrease the speed on these motors, FD and FB. So what happens is the aerodynamic drag NB and then D decrease, and the aerodynamic drag of NA and NC increases, which gives you a net overall drag, a net yaw moment N that would turn it to the right. So basically that's how you turn in quadcopters. So it's not real obvious on how these things turn, but we'll look at the equations a little bit closer. So I actually wrote it in here. The moments NA, NB, NC, and ND are generated from the aerodynamic drag of the propellers. So that's how we could build a control force to turn the aircraft. So there's some other parameters here. So we have this length here and a width. And in our case, in our example here, this is a small quadcopter that we're working on, and this is 5 inches. The length is 5 inches and the width is 5 inches. So it's a symmetric one, but it doesn't necessarily have to be. So we have some crank arms here. Actually, this is 5 inches. This RA. So this is kind of like the radius, I guess we call it. Okay, so we have a length and a width, and we also have this RA. Okay, so there's some crank arms here. So we call this one up here. I'll try to zoom in on it a little bit so you can see a little bit better. So we have LAX and LAY. So when we generate a force from this motor, there's a crank arm here. So this force times this crank arm feeds into this moment. Likewise, this force times the crank arm LAY feeds into this moment L. So in our example, where there's an angle here, theta A, I guess theta of the arm, is 45 degrees. In our case, it's a very symmetrical quadcopter. It doesn't necessarily have to be that way for your, for whatever you come up with. If you were going to do your own design. So anyway, this is a diagram that you start off with that is important that we start off in trying to analyze the physics and dynamics of the quadcopter. So here's a side view diagram of the quadcopter, say in a hover. So again, we have our axes shown in red. This is our x-axis, and this is our y-axis, and this would be our z-axis, and this is the blue line is our airframe body, and we have motor A, motor B, motor C, and motor D with propellers on them. And motor A is going clockwise, and B is counterclockwise, motor C is clockwise, motor D is counterclockwise. So we generate these four forces: force A, force B, force C, and force D. So this would be a case if we're just hovering, we're just trying to counteract the weight of the airframe. And there's another little parameter here called height, which we use to try to compute the drag. So there's some aerodynamic drag that of the airframe also that has to do with the structure and things that stick out that kind of limits the speed, how fast we could go in this quadcopter. So V would be our forward velocity. So in this case, we would just be hovering. So if we wanted to go forward, this is the side view again, we would say pitch down the airframe. So it took the airframe and pitched it down a negative theta. And when we do that, we generate a force. There's a longitudinal force here. That's a resultant of the thrust vector of the motor. So in this case, if we're going forward, all the thrust of our propellers has tilted. So that would generate, if we summed up all these, that would generate an X force that would cause the airframe to move forward. So this is an example of pitching the nose down for forward flight. So this is the side view again. Again, this is our X, Y, and Z axis. Say with the airframe pitched down a little bit. If you look at the previous diagram, the airframe is not pitched down. It's like level. It's level in this plane here. So in this case, we pitched the whole airframe down. The axis remains kind of the same, but the airframe pitched down. Now this would be the axis, say, relative to Earth. And so we've pitched the airframe down, and that generates the forces for forward flight. So now we want to look at the physics a little bit. And so to get our body axis moments, this is the equation that'll do that. So we're trying to compute L, which is the roll. That would be the roll moment. So if we took this this distance here, LAY, and this is the force that's coming coming out of the page, say the force vector. So if we sum up the moments, the force of A times this crank arm plus the force of D times that crank arm minus the force of B times the crank arm and minus the force of C times the crank arm. That would give us our roll moment. Now to get our pitch moment, it's a similar equation. So we take our force of our length AX. So going this way is positive. So it's L AX FA plus LAX FB minus LAX FC minus LAX FD will give us our pitch moment. Now to get our yaw moment, the yaw moment is due to the aerodynamic drag difference of the propellers. So since we're moving, say, FA, force of A, the propeller's moving clockwise, that's going to generate a drag that would tend to turn the aircraft left. So that's why NA is negative here, and NB is positive because this motor's turning counterclockwise would tend to cause a drag that would tend to make the aircraft turn right. So the sum of our moments are NA plus NB minus NC plus ND. So this is to get our yaw moment, that would be the equation, the moment equation for the body axis, moment equation. The next thing is the mass moment of inertia that we need for our model of the quadcopter. So we're assuming a thin disk for mass moment of inertia. So basically it's a symmetrical thing here. So Ri, X, and Iy, that's the moment of inertia around X and Y are the same. It's symmetrical. So if you go to mass moment of inertia handbook, it would be the mass times Ra squared over 4. And if we looked in the handbook for our z-axis, our z isn't quite symmetrical the way X and Y is. It would be m times Ra squared over 2. And it's also good to have the mass moment of inertia for the propeller. So we assume our propeller is a slender rod. So we have our moment of inertia of the propeller is the mass of the propeller times the radius of the propeller squared over 12. So this would be the equation for the mass moment of inertia for the propeller. So now I'd like to introduce you to the spreadsheet here that I made. And so this spreadsheet is used to verify one point of a hand calculation. So the way this works is that the things in bold inputs are in this bold font. So anything that's bold is an input, and anything that's not bold is a computed value. So that's how I set up the spreadsheet. So what I do is I generally make one column, and things that are not bold, you just want a $sign after each letter. See, in this case, I want to get rid of that $sign in front of the B. So this way, when we copy the columns over, if we're doing a parametric variation, so you could do a parametric variation on any parameter that's in bold. So for example, the altitude is handled by this air density. So if you get a standard atmosphere table, this is the air density at sea level. So what you would do is put air density, say at 1,000 feet, it would be a lower number here, and you could add columns and cut and paste, and then vary, say, just the air density if you wanted to do a parametric variation on altitude. So anyway, so we're going to go through the 1 point calculation that's shown in this Word document and compare it against the spreadsheet. So this is for validation of the spreadsheet to verify that the calculations are correct. Okay, so we're going to go through that now. So we have the arm radius of the quadcopter. That's this parameter shown here. And in this case, it's 5 inches. It's a pretty small quadcopter. It's not so small that's impossible to work on, but small so it could maybe be a good indoor flyer. So if we want to compute this angle here is also a given. It's 45 degrees. So you can see the radius is bold, and theta A, the arm degree 45 degrees, is also bold. Now if you look underneath here, I also have it in radians. So radians is computed. So you just take the 45 degrees times pi over 180. So that'll give it to you in radians. So likewise, we have the airframe in inches, but we also need it in feet. So just divide it by 12, as you can see from the formula, to get it in feet. So we have some of the basic parameters. So for our crank arms, LAY and LAX, it's this radius times the cosine of the angle. So we have that over here. We have we're getting 0.2946 feet. So we take B15 is the radius and times the sine of the angle in radians. Over here is B17. So this gives us our crank arms in feet. So we wanted to get our crank arms because we need that for our moment equation. So another important parameter is the mass. So the mass of our quadcopter is 1 pound. That's over here we have our weight is 1 pound. So, but we need that. We need to get that in not in pound units, but we need to get it in these units of pound second squared per foot. So we have to divide it by the gravitational constant over here. And so we do that, and so we get 0.03108 pounds/second squared per foot to get the mass in the right units that we need to work in. So the next thing that would be good to compute is the moment of inertias. So we're going to do that now. So I'm going to go down on the spreadsheet here a little bit. So we're going to compute our X and Y mass moment of inertia of the quadcopter. That's our IX and IY, and that's going to be the mass times the radius squared over 4. So we have that also in our spreadsheet. This is the radius squared times the mass over 4. And so we get a pretty small number. The units are foot/pound/second squared. So for I, X, and IY, we get 0.001349. So the moment inertias are very, very small, because this is just a little toy, which makes it much more difficult to control. So that's why we have to use like angular rate feedback, and because it would be impossible to control by hand with that with that small moment of inertia. So as you can see here, our IZ is twice of what IX and IY, because it's mass times the radius squared over 2. So we get 0.002698 foot/pound/second squared. So the next thing we have is the mass of the propeller. So these propellers are very light. I'm just guessing it's 0.01 pounds. So this is our mass of the propeller, and we have that over here in the spreadsheet. So all we do is we take the mass of the propeller, the weight of a single propeller, and divide that by 32.174, and we get 3.1081 times 10 to the minus 4 pounds/second squared over foot. So the radius of our propeller is 3 inches, which is 0.25 feet. So this is our let's see. Well, our input here is the diameter, and is 6 inches. So that's some bold. So to get the radius, we just divide that by 2. I want to get rid of the $ in front of the first B, because when it'll make it easier. I'll have to go through the spreadsheet again to make sure that's the case. So anyway, so we have our radius of the propeller is 3 inches. So the mass moment of inertia of our propeller is over here, and we use a spreadsheet to compute it. So it's the mass of the propeller times the radius of the propeller squared, which is 0.25 feet, over 12. So we get 1.6188 times 10 to the minus 6 foot/pound/second squared. In this example, we have 4 two-bladed 6-inch by 3 propellers for the quadcopter that are spinning at an RPM that is sufficient to be able to lift the weight of the quadcopter. This RPM will be computed in this example. The chord of the blade is 0.6 inches. So that chord, that 0.6 inches, is kind of like the average chord of the blade. So you could kind of estimate that. This is a simplified analysis. So it's the idea is to be able to do this on the back of the envelope, but the equations do get a little complicated. So just using a spreadsheet is probably good enough, rather than do whole bunches of elaborate blade element models and simulation. This is kind of like a simplified analysis, but you would need a spreadsheet rather than doing it on the back of an envelope, although you could probably do it on the back of an envelope. But anyway, so we have so these propellers, the way you buy propeller, you buy it by the diameter, and then you have this pitch displacement number. So the pitch displacement is 3 for these propellers I happen to have. So for every revolution of the propeller, 3 inches of air is displaced. So it's kind of like a screw constant. It's like the displacement constant. Sometimes they call it advance ratio. It's the how much air you're pulling through that blade per revolution. So we have 4 two-bladed propellers. That we could have 3-bladed. We could that would be a variation, say, if we're doing a parametric analysis. So we're going to go through this example, and go through what it looks like for this particular propeller. So again, here's our spreadsheet, and anything in bold is an input, and things that aren't bold are computed. So we have a 6-inch diameter blade. That's our input here on the spreadsheet. There's our 6 there. And having little problems with Excel here. Okay, so our radius is 3 over here. And our another input, this happens to be a 3 inches per rev, so it displaces 3 inches of air per revolution. This is our propeller inflow. And then we have the chord of the propeller. This is kind of estimated. The propeller's got a variable chord, but this is kind of an estimate. So our propeller diameter here is 6 inches, and our radius is 3 inches, which is 0.25 feet, and our inflow is 3 inches per rev, and our chord is 0.6 inches, which is over here. That's our 0.6 inches there. Okay, so the surface area of our propeller, our chord is 0.05, and our radius, I guess per blade, our surface area would be 0.25 times 0.05, which is 0.125 feet. So let's see, can we find that in our computations for that's over here. This is our surface area right here. So we're trying to verify the spreadsheet calculation with one-hand calculation. So we want to get the pitch of the propeller. So there's a little equation. The tangent of the pitch angle is equal to this this inflow, which is 3 over pi times the diameter. So from that, the average pitch of the blade is 9.043 degrees, or 0.1578 radians, and that's also computed over here. Here's our blade pitch in degrees, and this is it in radians over here. So to get it, we take the inverse tangent of 3 over pi times 6. So that's what we get. We get our average pitch is 0.1578 radians of this blade. So I have a little section here I call it single propeller parameters. So this is parameters of a single propeller. Although we have 4 propellers, this would be like the case if all 4 propellers were the same in a hover, and it's the case. It's trying to compute what RPM do we need to be able to lift just the weight of the quadcopter. So now we'll get into a little bit of the aerodynamics. So we have our density of air at sea level, and that's an input. That's 0.0023769 pounds second square per foot to the 4th power, and you can get that from a standard atmosphere table. And if we go back, that's one of our main inputs, basic parameters. That's over here. And then we have some coefficients of lift. Okay, and drag. Okay, so we have the coefficient of lift for a flat plate. So we could assume it's just 2 pi. If you don't know what the coefficient of lift is, just use 2 pi. The airfoil does make a slight difference, but it's not big enough to impact this analysis. If you did have a better coefficient of lift, you could put that in here at this point here. And then we have coefficient of drag for an airfoil, and I got this out of just a handbook. So it's 0.045. So that's over here. And coefficient of drag for a flat plate. So that's kind of like a flat plate that's going through the air is 1.28. So that's in here. So where PC is the chord of the propeller, the surface area of the propeller is, so the surface area of the propeller, PA, is equal to the radius of the propeller times the chord of the propeller. So this would give us the surface area of each propeller blade. So now we're trying to get the average dynamic pressure on the blade, And I had previously given a video on how this equation is derived. So our average dynamic pressure is equal to rho omega squared times the radius of the propeller squared over 6. So this is the average dynamic pressure for each propeller blade. It's a way, rather than having to do a blade element model, this is a simplification that allows me to compute the average dynamic pressure that each propeller sees. So X could be A, B, C, or D. So that's what X is equal to. And where X is equal to A, B, C, D, the force for each propeller blade is a coefficient of lift times the average dynamic pressure times the surface area of the propeller blade. This is like each blade. So like for a so this is just for a blade. Okay, these propellers are two-bladed propellers. So this is just for a single blade. Okay, so this is the coefficient lift times the average dynamic pressure times the surface area of that blade times the pitch angle. So that would be the force generated from the propeller. So for a two-bladed propeller, the thrust it's equal to F2, I call it F2x, is equal to 2 times the coefficient of lift times the average dynamic pressure times the surface area times the blade angle. So that's this equation times 2. And I did some other simplifications. I call this a force gain. So like the thrust is a function, it winds up being a function of the angular rate of the blade squared. So this could, PFG could kind of be like a gain, a propeller force gain. So we're going to compute all that. That'll be helpful in some of the analysis that we do. So if we dig into this a little more, the force gain of the propeller as a function of its rotational speed squared is, so we dig into this equation a little bit more. If we expand it out, it's 2 times the coefficient of lift, and this is our average dynamic pressure. This is the radius of the propeller. This is the P is C is the chord of the propeller times the pitch angle. I believe P is C is right, the chord of the propeller. Okay, if we expand this out a little bit, now we'll expand this equation to simplify it a little bit. So from that we can get our force gain. The propeller force gain is equal to the coefficient of lift times the density of air times the radius of the propeller cubed times the chord of the propeller times the pitch of the propeller over 3. So this is our force gain of the propeller. So we're going through the equations of the propeller. That's important if we're doing these like back of the envelope type of calculations for our little quadcopter. So anyway, we want to compute what's the RPM of the propellers that we need to be able to lift the weight of the aircraft. So what we do is we take the force required over 4 times this force gain, take the square root of that, and that'll give us the speed that we need to be able to lift the weight of the quadcopter. So we're going to go through these equations a little bit in our spreadsheet a little bit further. So I have these 2 parameters like for drag. I call it D1 and D2. So D1 drag is the kind of like, sometimes they talk about like profile drag and induced drag. I'm looking at it a little bit different. I call it D1. D1 is kind of more of maybe the profile drag, and D2 is equivalent to induced drag. So D1 is just the drag from the airfoil, and D2 is the drag that's created as a function of lift. So anyway, so our D1 drag is our airfoil coefficient of drag times our average dynamic pressure times the surface area, and our D2 drag is the flat plate drag times our dynamic pressure times the surface area times the pitch of the blade. So this is our D1 drag for each propeller blade and D2 drag for each propeller blade. So the total drag for a two-bladed propeller is 2 times this plus 2 times that. This would give us our total drag. So we're gonna look at those equations. We're gonna look through the example a little bit more to show you how that's all computed in here. So the torque on the propeller is okay. So I did do a video on propellers previously that go into the details of this. So it's actually the center of pressure is 3/4 of the radius of the propeller. So if you take the drag, the total drag, and you multiply that by 3/4 of the radius, that'll give us a torque on the propeller. So the power required for the propeller is the torque times the speed of the propeller. So that's what this equation is over here. So we're going to go through some of these calculations. So this is our single propeller sample calculations. So this is assume all 4 motors have the same command. This is our little test case, our test point. So the propeller force gain, this is the equation for it. And we have it in our spreadsheet here, computed in our spreadsheet. And I'm just checking to make sure we get the same result. I did this with a calculator versus the spreadsheet. So we get 6.1384 times 10 to the minus 7 pounds per radian per second squared. So this would be the force gain computed, and it's computed over here. Here's the formula again. I know you can't see the whole formula here. I might be able to bring this down. There it is a little bit, so you can see the whole formula there. Okay, so now the motor speed required for all 4 motors to lift the weight of the quadcopter. So our weight is 1 pound, and we divide that by 4 times this force gain to take the square root of that. So we get 6,094.18 RPM. Being these motors can go up to about 12,000 RPM, that's a pretty good, that gives us twice the of what we need in RPM to be able to lift the weight of the aircraft. So I have that equation also over here in the spreadsheet in radians per second, and then we convert it to RPM over here. So that's it in radians per second and RPM. So our average dynamic pressure here, now that we have what RPM or what speed is required to be able to lift the weight, our average dynamic pressure is the density of air times the speed here, which is 638.18 radians per second, and we have to square that. And this is the radius of the propeller squared over 6. So our average dynamic pressure is 10.0839 pounds per square foot. So this is just a check for a single propeller thrust. That would be 1/4 of the quadcopter weight, which is 1/4 of a pound since the whole quadcopter weighs a pound. So if we take our force gain and we multiply that by the speed of one propeller, we get 0.25 pounds. And I believe that's this parameter right here in our equation. So there's the formula there. So it comes in handy to do like at least one check of hand calculations versus the spreadsheet. So now we're going to compute the D1 drag of a single propeller. And that's equal, we went back, if we go back to the equation, it's 2 times the profile drag, the airfoil drag, times the average dynamic pressure, times the surface area of the propeller. So that drag is 0.0133 pounds, and we have that in here. This is the formula over here. So that matches. And then the D2 drag, that's more like the induced drag. This is more, D1 is like profile drag. So it's equal to 2 times the coefficient of drag of a flat plate times the dynamic pressure times the surface area of the propeller times the pitch angle of the propeller. So the pitch angle's fixed on this propeller. So if we go through the equations, we get 0.0509 pounds. So that's this parameter over here in the spreadsheet. So we have the 0.509 pounds. So the total drag for a single propeller is this plus this. So it's equal to 0.0623 pounds. So that's it over here. So we just add those two together. So the torque for a single propeller is 3/4 times the radius of the propeller times the drag. So it ends up being 3/4 times 0.25 times the drag force is equal to 0.01168 foot-pounds. So that's over here. So now the power for a single propeller, so we could compute the power now, is equal to the torque times the speed. So if we take, so this is the power for a single propeller just to lift the weight. So it becomes 0.01168 foot-pounds times 638.18 radians per second is equal to 7.4516 foot-pounds per second. So that's our drag in those units. Now if we want to, so we know 1 horsepower is equal to 550 foot-pounds per second is equal to 746 watts. So if we want to convert that to horsepower and watts for this little propeller here, we get 0.01355 horsepower. So this is a 5-inch toy helicopter. So that's equal to 10.1071 watts. So the power for all 4 propellers is 4 times that. So we get 40.4245 watts. That's quite a bit of power for a little thing like that. So one interesting thing we could do now, we could do some computations on our battery. So our battery we have is a given, it's a 11.1 volt DC battery, and the battery is rated for 0.95 amp hours when I look at the label on this battery. So just in trying to compute the battery life, if I take the voltage times the amp hours and divide that by the power, it's saying that battery should last 0.26 hours just to lift the helicopter. So that's telling me, yeah, maybe I have 15 minutes. I could run that battery for 15 minutes before I have to charge that up again if everything goes well. If there's no other inputs going into the battery, it's just doing a hover. So anyway, that's a way to estimate your battery life for the quadcopter. So next we're going to look at what happens if we have the 4 propellers have different commands. So this is the multiple propeller commands where the commands are different between the 4 motors. So this is just a test case to do one point, a hand calculation point. So let's say the motors are commanded to run at a certain RPM. So each motor A, B, C, and D will get a RPM command to maneuver the aircraft. So we have some RPM changes to maneuver. So in this test case, this is the RPM required just to hover to lift the weight of the aircraft. So let's say I gave it, this is arbitrary, I just picked 100, 200, 300, 400 just to do these sample calculations. So let's say our RPM change to pitch down the aircraft, the quadcopter, is 100 RPM, and to roll rate is 200 RPM, and to yaw rate is 300 RPM, and the vertical command change is 400 RPM. So the way the equations work, this is the individual motors A, B, C, and D. So this omega here, this command is a command just to lift the weight. So there's signs here, and this follows what I have to do. I have to reduce the RPM on A and B to pitch down, but increase it on C and D to pitch up. So you can go through and verify these signs here. The signs. So this is the basic equations you would use for pitch, roll, vertical, and yaw. So this is the mixing done to provide these commands. These are RPM commands to the 4 motors. I need to provide 4 commands to each of the motors to maneuver the aircraft. So this is just a sample that's done to arbitrary, just to get some numbers that I could put into the spreadsheet to get a test case, a test point. So if I plug these in to the equations, I get, so we'll go to the spreadsheet again. I have the multiple case. So now these are inputs. So you see how these are bold? So that means these are inputs. And anything that's not bold is an output. So now our omega A is this RPM, omega B is this RPM, omega C is this RPM. And here we'll put the comma in there. And this omega D is this RPM. So I'm going to save that. And this is our average RPM over here. So the average should be what's required to lift the weight of the aircraft. So I have that all in here. So I have it in terms of RPM and radians per second. So this is just to get one test point for the case where I have 4 different inputs. I have a pitch input, a roll input, a vertical input, and a yaw input. So now in this case, the dynamic pressure of each propeller, of each of the 4 propellers, is going to be a little bit different because of these commands. So I went through and I computed the dynamic pressure for motor A, B, C, D, or propeller A, B, C, and D. And I have that in the spreadsheet over here. So these should all match. So I have 13.665 in there. And I was able to verify that these all match. So the next piece is to get the thrust of each propeller. So the thrust, I can now compute that because I know the dynamic pressure on the blades. So the dynamic pressure equation again was 2 times the coefficient of lift times the average dynamic pressure times the surface area times the pitch angle. These are all pretty much constants. The only thing that changes is the dynamic pressure because the speed of the blades are different. So that's all computed here, and it matches with these. It matches in here, and these 4 parameters here, and I also have an average dynamic pressure and the total force. So it's taken a little bit more than 1 pound in this case of thrust to provide this command power. So now we're going to compute the roll moment from this command input over here, and we went through that equation previously where it's equal to this crank arm LAY times all these forces. So our roll moment comes to 0.02108 foot-pounds, and then we're going to compute our pitch moment, and in this case our pitch moment comes to minus 0.01126 foot-pounds. So the spreadsheet matches the calculation for our pitch moment. So now we're going to compute the drag 1 for each propeller blade, and that's over here and here. Let's see. Okay, 1, 2, 3. So this is our D1 drag here and here. So we get 0.0061, 0.0064, 0.0057, 0.0077 pounds. And then we compute our D2 drag over here. So our D2 drag is done over here in the spreadsheet. So we get 0.0272, 0.0289, 0.0255, 0.0345. So now we want to get the total drag for each propeller. So it's the sum of these two. This is our total drag. So we're verifying it with the spreadsheet. So our total drag for each propeller, this is the aerodynamic drag, is 0.0664, 0.0707, 0.0623, 0.0844, and you can see the equations here should match over here. It's 2 times the number of blades times the D1 and D2 drag, and then we can get the total torque. The total torque on each propeller is over here. Here it's shown as yaw moment, but it's torque over here. So we get 0.01246, 0.0326, 0.01168, 0.01582 foot-pounds are the units. So now our yaw moment is, we looked at that equation previously, was equal to minus the A plus the B minus the C plus the D, because of the counterclockwise and clockwise rotation of the propeller. So we get 0.00495. That's over here, and it matches the spreadsheet. So now we can compute the power for each propeller over here. So we have that, and we want to make sure that it matches on our spreadsheet. So we're going to bring the spreadsheet up here. So and this is going to be in watts. So this is our power here. So just want to make sure that for this one point it matches. So when we go on and do parametric variations, we can see how that works out. So we have 11.1352 and 2.2308 and 10.1071 and 15.9437. So they all match. So the total power for all the propellers, if we add that all up, is 49.4168 watts. So that's the parameter over here. And you can see I'm just adding them all up over here. So the next thing we want to do is look a little bit at the performance. How do we evaluate the performance? So we have, so we want to get an estimate of the drag of the airframe. Let's just see how fast we can move this aircraft. So the width of the airframe is 0.5893 feet, and the length of the airframe is 0.5893 feet also, and we also have a height. So these are a result of the radius. So we'll go back and take a quick look at that. So this is our length and our width, and that's these are a function of the geometry, since it's a 5-inch radius. So we could compute that. It's let's see, we have yeah, it's basically this, crank arm times 2. So that's what we have over there, and we're saying the height is about 3 inches. So that's where we get 0.25 feet. So we're estimating that when this maneuvers, it's about 10 degrees in pitch and roll attitude. So there's some surface areas. So this is an input, or roll and pitch attitude. So these are just kind of guesses of what the attitude is when the aircraft is maneuvering. So we put in an airspeed, a forward airspeed of 16 knots over here, and that's an input to our spreadsheet. So what we're trying to do is take a quick look at the performance to try to figure out, how fast can this airframe go at this pitch attitude. So it might not be the case that the pitch attitude is this, but we'll get some test data and look at it to look at the performance of this. And when we go further with simulation, then we can look at it a little closer. So we're saying our forward airspeed is 16 knots, and let's say our lateral airspeed is also 16 knots. So we have that as an input also. So that winds up being 27 feet per second. So there's a dynamic pressure that's generated from the motion of the aircraft. So we want to compute that. So the dynamic pressure at 16 knots is 0.8667 pounds per square foot. So it just so happens that we're moving forward 16 knots and laterally 16 knots in this case. So we're just trying to get a snapshot. This is just for our test point for our calculations. So we're going to we also have a D1 and a D2 drag for longitudinal drag, lateral drag, and again this is assuming the flat plate again. So this would be like our longitudinal drag, and we also have a lateral drag also. So we'll look at that. Let's see. So we have our D1 longitudinal drag over here. So being this isn't an airfoil, the body of the is just a flat plate. So we're using our coefficient of drag for a flat plate. So notice how the D2 drag has the same value as the D1 drag, except it's pounds per radian, because that's the drag, that's a function of the pitch attitude or roll attitude. So our total drag is going to add up. We include that angle. It was at 10 degrees. So that's the numbers here for our total lateral drag and our total longitudinal drag. So we get 0.1919 pounds for each one of those. So the estimated longitudinal force from the props, we know our thrust, our total thrust is 0.114 pounds. That times the 10 degrees is 0.1978. So that's over here. So we have a slight, at 16 knots, we're computing that this aircraft might be able to go up to 16 knots. So we're computing, we have a slight residual X force and Y force, and residual Z force. So this is how we're saying it's feasible that this aircraft may be able to go up to 16 knots. We'll have to simulate it a little further and see, what it could really do at this point. But this is just a guess, like a back of the envelope type of calculation. So we have our total forces and moments, and our accelerations, X accelerations, and Y and Z accelerations. So we're saying for 10 seconds, with this case, in 10 seconds, our velocity, after 10 seconds, forward velocity builds up to 28.9 feet per second. So this is like a little integration we're doing in the spreadsheet to compute that. And our lateral velocity is 0.19 feet per second, and our vertical velocity, this negative, is going up, so it's climbing 44.83 feet per second. Now look how big these angular velocities are huge at this point. That's why we need to use angular rate feedback. So there's some hand calculations. This is our hand calculations we're doing. These residual forces again, which were up here, and so we're gonna do some simulation later on and show you how that might work. So you could see these after 10 seconds, our angular velocities are very high. So it's saying when we're actually dividing it by the moment of inertia, which is very small for such a small little toy aircraft. So that's why we need to do rate feedback and put a lot of control laws into this to try to stabilize it. So I want to get into the equations of motion for the 6 degree of freedom aircraft model that you could use. So generally, I want to talk about that a little bit. So generally, the equations of motion for anything, whether it's a little quadcopter toy, a brick, whatever you're trying to model, it might be something like this. So we have this is our longitudinal equation and our X force, and this is our lateral equation, linear lateral equation. And I'm not going to get into the details. If you get a book on aircraft dynamics, you'll see this over and over again. But this is the basic equations I'm using to model this. So this is our vertical equation in the Z direction. So we also have our equation. This is our around our x-axis. So this is our roll equation over here, and then we have our pitch equation over here, and we're going to have a yaw equation. I'm going to talk a little bit about some of the simplifications. Okay, so some of these forces are cross components. Some of it's from gravity, but anyway, for a quadcopter, so one thing we have is that these are the gyroscopic forces from the propellers. Okay, so but what happens in this quadcopter, they all cancel out. So what it is that note since this term angular velocities always sums to 0, the gyroscopic torques can be ignored to simplify the equations of motion. So for our x equation, this whole term equals 0. So we could simplify this. We could get rid of this whole term here. All the gyroscopic forces cancel. So in this case, it's a simplification. If for some reason they didn't cancel and you wanted a more complicated model, you could leave this in to see what the effects are. But for our simplified model, it's basically simplifies to this over here. So this would be our roll equation here. And likewise, for our pitch equation, it's the same deal where these the gyroscopic forces cancel out. So it simplifies our pitch equation here. Now, also the angular accelerations cancel. So when we accelerate one motor one way, we accelerate the other motor the opposite way. So I guess a lot of thought in the way you maneuver, especially in yaw for a quadcopter. It's not people might think that it has to do with the change in angular acceleration, but they all cancel. It's possible that they might not if you set it up that way, but normally to prevent the aircraft from falling out of the sky, you want to when you increase one, you want to decrease the other one. So our angular acceleration terms equals 0. So this would be the equation, our yaw equation over here. And so another thing is because we have symmetry, Ix is equal to Iy. So this term cancels and goes to 0, and this term cancels and goes to 0. So these equal 0 and these equal 0. Likewise, this term is equal to 0 in our, if we go back to our pitch equation and our roll equation, this goes to 0. So we could simplify our yaw equation, becomes very simple, and it's just IZR dot equals N. So the only force we have from N is due to the aerodynamic drag. So it's only the aerodynamic drag that's used to turn the directional axis of a quadcopter. So we have also have our body axis forces. X is equal to this would be like due to our drag in the X and Y direction, and this is our thrust, our total thrust. So we had what we could do to figure out our Euler rates in our simulation. This is one way of doing it. So we have a 6 degree of freedom model, but we also add another 6 derivatives here that we could add to get our X, Y, and Z position and our Euler angles. So this would be another way of doing it. So I just wanted to briefly touch on a way to simulate this if you were going to do a full simulation, but that gets into more details. That's where you start needing also to have the control laws, which we don't have yet. This would be like considered an open loop type simulation for what we have here so far. So anyway, well, thanks for watching this. I just wanted to go through this. It's very it gets a little complicated, but this is a simplification if you wanted to get into designing your own quadcopters and you wanted to do it from an engineering point of view aspect rather than a trial and error method to increase the performance or optimize your design. This is a start to it. So thanks for watching this. Bye now.